From the earliest moments of human curiosity, nature has appeared fragmented. We feel gravity as a constant downward pull, watch lightning split the sky as electricity, sense magnetism guiding a compass, and learn that deep inside atoms, powerful nuclear forces hold matter. Together, for centuries, these forces were treated as separate actors on nature's stage, each with its own rules and behaviors. Yet modern physics has slowly peeled back this layered illusion, revealing a far more profound truth. What we call different forces may be expressions of a single, unified foundation. The idea that all fundamental forces are one is not a poetic metaphor, but a conclusion emerging from decades of careful observation, mathematical insight, and experimental discovery. The journey toward unity began quietly, almost accidentally. In the 19th century, electricity and magnetism were studied as unrelated phenomena. Electricity flowed through wires, magnetism lived in lodestones and compass needles. It was only when scientists like Michael Faraday and James Clerk Maxwell began to see patterns linking electric currents and magnetic fields that a deeper connection emerged. Maxwell's equations did more than describe known effects. They revealed that electricity and magnetism were inseparable aspects of one electromagnetic force. Light itself turned out to be an electromagnetic wave, meaning that vision, radio signals, and X-rays all shared the same underlying origin. This was the first great hint that nature prefers unity over division. As physics moved into the 20th century, the pattern repeated on a deeper level. The discovery of the atomic nucleus exposed forces far stronger than electromagnetism. The strong nuclear force bound protons and neutrons together, while the weak nuclear force governed radioactive decay. These forces seemed utterly different in strength and range, yet quantum theory revealed surprising similarities in their mathematical structure. When physicists explored these forces at extremely high energies, conditions similar to those just after the birth of the universe, they found that the boundaries between them began to blur. Electromagnetism and the weak nuclear force merged into a single electroweak force, suggesting that what we observe today as distinct interactions were once unified. This unification is not merely theoretical elegance. It is supported by experiments that precisely match predictions made by unified equations. Particle accelerators recreate tiny echoes of the early universe, smashing particles together at enormous energies. In these collisions, forces behave as if they are different faces of the same underlying interaction. The success of these predictions strengthens the idea that separation is not fundamental, but conditional, shaped by the energy and structure of the universe itself. At the heart of this unity lies the quantum field perspective. In this view, the universe is not built from particles alone, but from fields that exist everywhere, even in the emptiness of space. Each fundamental force corresponds to a field, and particles are excitations of these fields. The remarkable insight is that these fields may themselves be manifestations of a deeper, more unified field structure. Forces arise from the way these fields interact, fluctuate, and exchange energy. The differences we observe are like different notes played on the same instrument, shaped by how the universe is tuned. Symmetry provides the guiding principle behind this idea. In physics, symmetry does not simply mean visual balance. It means that the laws of nature remain unchanged under certain transformations. Unified theories are built on powerful symmetries that treat forces as equivalent at a fundamental level. In the earliest moments after the Big Bang, the universe may have existed in a highly symmetrical state, governed by one unified force. As the universe expanded and cooled, this symmetry broke, much like a perfectly smooth surface cracking as it freezes. Each crack defined a new force, distinct in behavior but rooted in the same original structure. This process of symmetry breaking explains why forces differ so dramatically in strength today. Gravity is extraordinarily weak compared to the strong nuclear force, yet it dominates cosmic structures because of its infinite range. From a unification perspective, gravity's weakness may itself be a clue, pointing to how it separated from the other forces under conditions we do not yet fully understand. The challenge of unifying gravity with quantum forces remains one of the greatest unsolved problems in physics, but even here, patterns suggest that gravity may not be an outsider, only a deeply hidden participant in the same underlying unity. The idea of unity reshapes our understanding of reality. Forces no longer act as independent entities pushing and pulling objects through empty space. Instead, they emerge from relationships within a continuous quantum fabric. When a force acts, it is not something being sent from one object to another. It is a reconfiguration of the underlying fields that connect them. In this sense, the universe behaves less like a machine with separate parts, and more like a single, interconnected system, responding as a whole. This unified view also changes how we see matter itself. If forces are unified, then the particles that feel these forces are not isolated building blocks, but expressions of the same underlying principles. Mass, charge, and spin become properties defined by how particles interact with unified fields. The Higgs field, for example, reveals how mass itself can arise from interaction with a pervasive quantum field, further reinforcing the idea that what we experience as distinct properties emerge from a shared foundation. Beyond equations and experiments, the unity of forces carries philosophical weight. It suggests that complexity is not fundamental, but emergent. The rich diversity of the universe, from atoms to galaxies, unfolds from simple underlying rules. This does not diminish mystery, it deepens it. If everything arises from one source, then understanding that source becomes the ultimate scientific and intellectual challenge. Each step toward unification is not just a technical achievement, but a glimpse into the deep order of existence. As scientists continue searching for a more complete unification, theories such as grand unification and quantum gravity push the boundaries of knowledge. These ideas propose that at unimaginable energies, all forces converge into one. While experimental confirmation remains elusive, the consistency of this idea with everything we have learned so far keeps it alive. History shows that whenever physics has uncovered a deeper layer of reality, unity has replaced division. The unity of all fundamental forces is not a finished story, but an unfolding one. It stands as a reminder that nature often hides its simplicity beneath layers of apparent difference. What we perceive as separate forces shaping the cosmos may be shadows of a single invisible source, a unified quantum foundation from which all interactions flow. In recognizing this, we move closer to understanding not just how the universe works, but why it holds together at all. When we look around, the world appears solid, tangible, and well-defined. Objects seem to exist on their own, occupying space like separate pieces on a vast cosmic board. Even forces feel like actions between things, a pull here, a push there. Yet beneath this familiar picture lies a radically different reality, one that modern physics has uncovered with increasing clarity. At the deepest level, nature is not built from objects, but from invisible quantum fields that permeate all of space. These fields are not background scenery. They are the stage, the actors, and the script all at once. Everything we observe emerges from their subtle activity. The idea of fields is not new. Classical physics already described electric and magnetic fields spreading through space, allowing forces to act without physical contact. But quantum theory transformed this concept into something far more profound. In the quantum view, fields are fundamental, while particles are secondary. An electron is not a tiny bead traveling through emptiness. It is a localized vibration in an electron field that exists everywhere. The same is true for quarks, photons, and every other particle known to physics. Matter itself is an expression of fields, temporarily shaped into forms we recognize. What makes this view so striking is that these fields exist even in the absence of particles. Empty space is not empty. It seethes with restless energy, fluctuating even at absolute zero temperature. These quantum fluctuations are not theoretical curiosities. They produce measurable effects, such as forces between closely spaced metal plates and tiny shifts in atomic energy levels. Space, once thought to be a passive void, is revealed as an active medium with structure and energy of its own. From this perspective, forces are not separate agents acting across space, but consequences of how quantum fields interact. When two charged particles repel each other, they are responding to disturbances in an electromagnetic field that links them. When nuclear forces bind protons together, it is the strong field rearranging itself to create stability. Even light is nothing more than a ripple in a field, carrying energy and information across the universe. The diversity of forces reflects the diversity of fields, yet the deeper insight is that these fields may themselves arise from an even more unified foundation. Quantum field theory provides the mathematical language for this hidden world. It combines quantum mechanics with special relativity, allowing fields to create and annihilate particles as energy flows through them. In this framework, interactions occur through the exchange of field excitations, making forces dynamic and relational rather than static. The success of this theory is extraordinary. Its predictions match experiments to astonishing precision, suggesting that this invisible field-based reality is not an abstraction, but a faithful description of nature. The notion that fields underlie everything challenges intuition. We are accustomed to thinking of matter as primary and space as empty. Quantum fields invert this picture. Space is full, and matter is what happens when fields vibrate in specific ways. This shift has profound implications. It means that the properties of particles, such as mass and charge, are not intrinsic in the classical sense. They arise from how particles interact with surrounding fields. The Higgs field is a striking example, showing that mass itself can emerge from interaction with a pervasive quantum field that fills the universe. These fields do not exist in isolation. They overlap, interact, and influence one another constantly. The vacuum of space is therefore a complex environment where fields coexist and exchange energy. Under extreme conditions, such as those in the early universe or inside powerful particle accelerators, these interactions reveal deeper symmetries. Fields that appear distinct at low energies behave as if they are different aspects of a single structure at high energies. This behavior strengthens the idea that the many fields we observe may be manifestations of one underlying quantum reality. The early universe offers a natural laboratory for this idea. Just after the Big Bang, temperatures and energies were unimaginably high. Under those conditions, the distinctions between fields may not have existed. As the universe expanded and cooled, fields differentiated, taking on unique roles and behaviors. This process shaped the forces and particles we see today. What appears fundamental to us may be a frozen outcome of cosmic evolution, not the deepest layer of reality. Understanding quantum fields also reshapes our sense of causality and connection. Because fields extend throughout space, interactions are not confined to isolated points. Changes in one region can influence others through the field's structure. This interconnectedness is subtle, obeying strict physical laws, yet it suggests that the universe is woven together more tightly than classical pictures imply. At the quantum level, separation is not absolute. Everything exists within the same field-based fabric. This hidden foundation has practical consequences as well. Technologies that define modern life, from semiconductors to lasers, rely on quantum field principles, even if indirectly. Our ability to manipulate matter and energy depends on understanding how fields behave. As research advances, deeper knowledge of quantum fields may unlock new technologies, perhaps even new ways of controlling forces themselves. Despite its success, the quantum field picture remains incomplete. Gravity resists full integration into this framework, hinting that our understanding of fields may need to evolve further. Some theories suggest that space and time themselves could emerge from an even deeper level, where fields are not defined on space, but give rise to it. If true, the invisible foundation of reality would be more abstract and more unified than anything yet imagined. The idea that quantum fields form the hidden foundation of reality is both unsettling and inspiring. It strips away the comforting solidity of the world, replacing it with a dynamic, invisible web of activity. Yet it also reveals a profound order beneath the surface, a simplicity that gives rise to complexity. Everything we see, touch, and experience may be the visible expression of fields quietly vibrating in the background, shaping the universe moment by moment. In this view, reality is not made of things, but of relationships. Fields connect every point in space, making the universe a continuous whole rather than a collection of parts. The forces we experience are not external influences, but internal features of this field-based structure. By uncovering this hidden foundation, physics has not reduced the universe to something smaller or colder. It has revealed it to be deeper, more interconnected, and more mysterious than ever before. For most of human history, forces were imagined as invisible hands acting on objects, pushing and pulling them through space. Gravity pulled stones to the ground, magnetism guided iron, and electricity leapt as sparks across gaps. These effects felt real and immediate, yet their true nature remained obscure. Modern physics has gradually replaced this picture with something far more subtle and surprising. Forces, it turns out, are not objects or substances traveling between things. They are expressions of vibration, patterns of motion within an underlying quantum reality that fills all of space. At the smallest scales, nothing is truly still. Quantum mechanics reveals a world in constant motion, even in conditions we would call perfectly calm. Particles cannot sit quietly at fixed positions with zero energy. Instead, they fluctuate, oscillate, and blur between possibilities. This restless behavior is not a flaw in measurement. It is a fundamental feature of nature. When this quantum restlessness is described in terms of fields rather than particles, vibration becomes the central idea. Fields vibrate, and those vibrations are what we observe as particles and forces. Consider light, one of the most familiar forces in our experience. Light is not a stream of tiny objects moving through emptiness, but a vibration of the electromagnetic field. Different colors correspond to different frequencies of vibration. When light exerts pressure or transfers energy, it is the effect of these vibrations interacting with matter. The same principle applies to other forces, though the vibrations are often hidden from direct perception. What we feel as attraction or repulsion is the result of oscillating fields adjusting to each other. This idea extends deep into the structure of matter. Inside atoms, electrons do not orbit nuclei like planets around a sun. Instead, they exist as standing wave patterns, stable vibrations of an electron field bound by electromagnetic interaction. The shapes of atomic orbitals, the rules governing chemical bonding, and the behavior of materials all arise from these vibrational patterns. Chemistry itself becomes a story of resonance and interference, rather than rigid mechanical motion. The strong nuclear force, which binds protons and neutrons together, also reveals its vibrational nature when examined closely. Protons and neutrons are not elementary. They are composed of quarks held together by the strong field. The force between quarks is carried by gluons, themselves excitations of the same field. These interactions are dynamic and constantly shifting. What appears as a stable particle is, in reality, a constantly vibrating system whose energy patterns create persistence. Even forces that seem static, like gravity, may have a vibrational interpretation. In modern theoretical frameworks, gravitational effects can be described in terms of ripples in the fabric of space-time itself. The detection of gravitational waves confirmed that massive events in the universe create vibrations that propagate across cosmic distances. Gravity, once thought to be the most classical of forces, now appears as another manifestation of oscillation, though in a geometric rather than field-theoretic form. Seeing forces as vibrations dissolves the boundary between matter and interaction. Matter is not something that forces act upon. Matter is shaped by forces continuously vibrating within it. Stability arises not from stillness, but from balance. Just as a musical note remains steady when vibrations are coherent, particles and structures persist when their underlying oscillations reinforce rather than cancel each other. This perspective also helps explain why forces have specific strengths and ranges. The frequency and mode of vibration determine how far an interaction extends and how strongly it couples to other systems. Electromagnetic vibrations can travel freely across space, giving the force infinite range. Strong force vibrations are confined, limiting their influence to the scale of atomic nuclei. These differences are not arbitrary. They reflect the allowed patterns within the underlying quantum framework. The early universe provides a dramatic illustration of this vibrational view. In the intense energy of the universe's first moments, vibrations were far more energetic and unified. Distinctions between forces had little meaning. As the universe expanded and cooled, vibration modes changed. Some frequencies became frozen out, others separated, leading to the distinct forces we observe today. What we now call different interactions may be remnants of a once unified vibrational spectrum. This idea resonates beyond physics into how we conceptualize reality itself. If everything is vibration, then separation is a matter of scale and pattern, not absolute division. Objects are regions where vibrations stabilize. Interactions are shifts in rhythm and phase. The universe becomes less like a collection of solid things and more like a vast, evolving symphony, where structure emerges from harmony and change. Understanding forces as vibrations also reframes the role of observation. Measuring a system means interacting with its vibrational state, altering it in subtle ways. This helps explain why observation plays such a central role in quantum mechanics. We are not passive spectators watching objects move. We are participants engaging with a dynamic field of oscillations. Technological advances increasingly exploit this insight. From controlling electron waves in semiconductors to manipulating vibrational states in quantum computing, modern technology depends on shaping and maintaining precise oscillations. The future may bring even deeper control, allowing us to engineer new forms of matter and interaction by tuning the vibrations at their foundation. The realization that forces are vibrations rather than objects challenges deeply held intuitions, but it offers a unifying vision. It suggests that beneath the apparent solidity of the world lies a continuous dance of energy and motion. Forces do not travel through space as separate entities. They are space vibrating, fields oscillating, reality expressing itself in motion. In embracing this view, physics moves closer to a deeper unity. Different forces become variations on a single theme, shaped by how and where vibrations occur. The universe reveals itself not as a static construction, but as an ongoing process, a living pattern of oscillation. What we experience as force is the music of the quantum world, playing endlessly beneath the surface of things. In the deepest layers of modern physics, symmetry is not an artistic idea or a visual preference. It is a governing principle that determines how nature behaves at its most fundamental level. Symmetry, in scientific terms, means that the laws of nature remain unchanged when viewed from different perspectives or under certain transformations. Rotate the universe, shift it in time, or change certain properties, and the underlying rules still hold. This quiet consistency is not just elegant, it is powerful. It is from symmetry, and more importantly from the breaking of symmetry, that the rich structure of the universe emerges. In the earliest moments after the birth of the universe, conditions were unimaginably extreme. Temperatures and energies were so high that distinctions we now take for granted had no meaning. Forces that appear different today may have been indistinguishable, governed by the same symmetrical laws. In that primordial state, nature was simpler, not in the sense of being empty, but in being unified. Everything followed the same rules, expressed through perfect symmetry. This early symmetry was not fragile. It was a natural consequence of extreme energy, where differences could not yet crystallize. As the universe expanded and cooled, this symmetry did not disappear all at once. Instead, it fractured in stages, like a perfectly balanced object slowly losing equilibrium. This process, known as symmetry breaking, is one of the most important ideas in modern physics. It explains how complexity can arise from simplicity without violating underlying laws. The rules remain the same, but the state of the system changes. A useful analogy is cooling water. Above freezing, water molecules move freely and look the same in every direction. Below freezing, they lock into a crystal lattice. The laws governing the molecules have not changed, but the symmetry of the system has. In the universe, symmetry breaking shaped the forces of nature. At very high energies, what we now call different forces may have been unified. As energy dropped, symmetries broke and forces separated. Each break introduced new distinctions, giving rise to new behaviors. This is why forces differ in strength and range today. The differences are not fundamental flaws or arbitrary features. They are the historical outcome of how symmetry unraveled as the universe evolved. This idea is not abstract speculation. It is supported by precise mathematical frameworks and experimental evidence. Particle physics shows that the properties of particles are tightly linked to symmetry principles. Charges, spins, and interactions are determined by how particles transform under symmetry operations. When symmetries are exact, particles behave in predictable, unified ways. When symmetries are broken, particles acquire different masses and interactions. The Higgs field plays a central role in this story, providing a mechanism by which symmetry breaks and particles gain mass without destroying the underlying order of physical laws. The power of symmetry lies in what it forbids as much as in what it allows. Certain interactions simply cannot occur if they would violate symmetry. This is why some particles are stable, why certain decays are rare, and why conservation laws exist. Energy conservation, momentum conservation, and charge conservation all arise from deep symmetries of space and time. These are not imposed rules, they are consequences of symmetry itself. When symmetry is exact, conservation is absolute. When symmetry is slightly broken, new phenomena become possible, but always within strict limits. Broken symmetry is especially important because it introduces direction and structure. In a perfectly symmetrical state, nothing stands out. There is no preferred orientation, no hierarchy, no differentiation. Breaking symmetry creates asymmetry, and asymmetry creates structure. It defines what is different from what, allowing particles to have mass, forces to have range, and matter to clump into stars and galaxies. Without broken symmetry, the universe would be uniform and featureless, governed by simple laws but devoid of complexity. This process also explains why the universe appears finely tuned. Many physical constants seem delicately balanced, allowing atoms, chemistry, and life to exist. From the symmetry perspective, these values are not arbitrary choices, but outcomes of how symmetry broke in the early universe. Small differences in the breaking process could have produced a very different cosmos. Our universe is one possible realization among many allowed by deeper symmetrical laws. This does not make it less meaningful. It makes it a natural outcome of a lawful process. Symmetry breaking also introduces time into the story. In a perfectly symmetrical universe, time would have no direction. The breaking of symmetry creates irreversible processes, giving rise to an arrow of time. As the universe cooled and structures formed, history became meaningful. Events happened in a particular order, and the past became distinct from the future. This temporal asymmetry is closely linked to the same processes that separated forces and gave particles their properties. On smaller scales, symmetry and its breaking govern the behavior of materials and phases of matter. Magnetism, superconductivity, and crystalline structures all arise from symmetry principles. When atoms arrange themselves in certain patterns, symmetries are broken, leading to new collective properties. These everyday examples mirror what happened on a cosmic scale, reinforcing the idea that the same principles operate everywhere, from the smallest particles to the largest structures. The elegance of this framework is that it preserves unity even in diversity. Although symmetries break, they are never completely lost. Traces of the original symmetry remain encoded in the laws of physics. This is why forces can sometimes merge under extreme conditions, and why particles can be related through mathematical transformations. The universe remembers its symmetrical origin, even as it expresses itself in asymmetric forms. From a documentary-style perspective, this story is one of quiet transformation rather than dramatic intervention. There was no external hand shaping the universe into complexity. The laws of nature, symmetric and consistent, allowed symmetry to break naturally as conditions changed. Complexity emerged not in spite of simplicity, but because of it. The same deep rules that unify everything also permit difference and structure. This understanding reshapes how we think about order and disorder. Broken symmetry is not chaos, it is organized difference. It creates patterns, hierarchies, and relationships. It explains why the universe is stable yet dynamic, ordered yet capable of change. Forces, particles, and structures are not independent inventions, but expressions of how symmetry unfolded over time. In the search for deeper theories, symmetry continues to guide physicists. New models are judged not only by their predictions, but by how naturally they incorporate symmetry principles. The hope is that at the deepest level, all forces and particles arise from a single symmetrical framework, with the universe we observe being one particular broken symmetry phase of that deeper reality. Seen this way, nature is not built from unrelated pieces. It is shaped by symmetry and sculpted by its breaking. The invisible rules of balance and transformation have guided the universe from a simple, unified beginning to the intricate, force-filled cosmos we inhabit. What appears complex and fragmented on the surface is, at its core, the result of symmetry quietly giving way, step by step, to the structured world we experience. Human beings have always searched for a single explanation behind the diversity of natural phenomena. Ancient thinkers imagined hidden elements, modern scientists speak of fundamental laws, but the impulse is the same: to find one coherent story that explains everything. In contemporary physics, this desire has taken the form of the quest for a single theory capable of uniting all forces and all matter under one mathematical and conceptual framework. This search is often described as the pursuit of a theory of everything, not because it would answer every question, but because it would describe the deepest level from which all physical behavior arises. The motivation for this quest is not philosophical ambition alone. It is driven by real gaps in our understanding. Today, physics rests on two extraordinarily successful, but fundamentally different frameworks. Quantum field theory describes the behavior of particles and forces at the smallest scales with astonishing accuracy. General relativity describes gravity and the structure of space and time on cosmic scales with equal success. Yet these two frameworks do not naturally fit together. When we try to apply quantum principles to gravity in extreme conditions, such as the center of black holes or the earliest moments of the universe, the equations break down. This mismatch suggests that both theories are incomplete reflections of a deeper, unified reality. The search for unity has a strong historical precedent. Each time physics has encountered apparently separate laws, deeper investigation has revealed connections. Electricity and magnetism merged into electromagnetism. Later, electromagnetism and the weak nuclear force were shown to be two aspects of a single interaction at high energies. These successes were not accidental. They followed a pattern in which mathematical consistency and experimental evidence pointed toward unification. This history gives physicists reason to believe that gravity, too, may eventually join the other forces within a single framework. One approach to this challenge imagines that the fundamental constituents of nature are not point-like particles, but tiny vibrating entities existing in higher, dimensional spaces. In such models, different particles and forces arise from different vibration patterns of the same underlying object. What appears as diversity is simply variation in expression. While these ideas remain unproven, they offer a powerful illustration of how unity might exist beneath apparent complexity. Another line of thought suggests that space and time themselves may not be fundamental. Instead, they could emerge from deeper quantum relationships. In this view, the geometry of the universe is not a fixed stage, but a dynamic result of underlying interactions. Gravity would then not be a force in the traditional sense, but a manifestation of how information and energy are organized at the most basic level. This perspective aligns with the broader theme that what we perceive as fundamental may be emergent, shaped by deeper principles. The quest for a unified theory is also constrained by experiment. Any successful framework must reproduce all known results of existing theories while predicting new phenomena that can be tested. This is an immense challenge. The energies at which full unification may become apparent are far beyond what current technology can reach. As a result, much of the search relies on indirect evidence, mathematical consistency, and subtle clues in existing data. Critics argue that this makes the quest speculative, yet history shows that bold theoretical exploration often precedes experimental confirmation. Beyond technical challenges, the pursuit of a single theory raises profound questions about the nature of explanation itself. Would such a theory truly explain everything, or merely shift the mystery to a deeper level? Even if all forces and particles are unified, we may still ask why that unified structure exists at all. Physics can describe how nature behaves with increasing precision, but the question of ultimate origin may remain open. The theory of everything, if achieved, would be a foundation, not a final answer. This search also reshapes how scientists think about simplicity and complexity. A unified theory may be mathematically simple, yet capable of generating immense complexity through its solutions. Just as simple equations can produce chaotic and intricate patterns, a single underlying law could give rise to the entire richness of the universe. This reinforces the idea that simplicity at the deepest level does not mean simplicity in appearance. The cultural impact of this quest should not be underestimated. The idea that all of nature might be understood through one framework captures the imagination far beyond physics. It echoes ancient ideas of unity and modern desires for coherence in a fragmented world. While scientific theories are not spiritual doctrines, they influence how we see our place in the universe. A unified theory would suggest that everything, from the smallest particle to the largest galaxy, is connected through the same underlying principles. At the same time, the search for unity encourages humility. Each generation of physicists has believed it stood close to a final understanding, only to discover new layers of complexity. The pursuit of a theory of everything may reveal not an endpoint, but a deeper landscape of questions. Unification could open doors to new mysteries, rather than closing the book on inquiry. From a documentary perspective, this quest is a human story as much as a scientific one. It involves creativity, debate, failure, and perseverance. Theoretical ideas are proposed, criticized, refined, and sometimes abandoned. Experimental results challenge assumptions and force revisions. Progress is slow and uncertain, yet driven by a shared conviction that nature is intelligible, that beneath its apparent chaos lies an underlying order waiting to be discovered. In practical terms, the benefits of unification are unpredictable. Past advances in fundamental physics have led to technologies that transformed society in ways no one anticipated. A deeper understanding of reality could one day lead to new forms of energy, communication, or computation. Or it may simply deepen our knowledge without immediate application. Both outcomes are valuable. Understanding the universe is itself a fundamental human achievement. As the search continues, the idea of a single theory of everything remains a guiding star rather than a completed map. It shapes research directions, inspires new mathematics, and challenges assumptions about space, time, and matter. Whether or not a final unified theory is ever achieved, the quest itself reveals something essential about science. It is driven by the belief that the universe, in all its complexity, is ultimately coherent. In this sense, the pursuit of unity is not about conquering nature with equations, but about listening carefully to what nature reveals. Each step toward unification is an attempt to hear a deeper harmony beneath the noise. The forces of the universe, once seen as separate and unrelated, increasingly appear as variations on a single theme. The theory of everything, if it exists, would not end the story of physics. It would mark the beginning of a new chapter, where understanding deepens and the invisible connections shaping reality become clearer than ever before.